Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. The alkenes. So the alkenes, you may well know from your pre-A-level chemistry, are a homologous series, which are classified as unsaturated. That is, they contain a carbon-carbon double bond, but at A-level you must be very clear that they contain one carbon-carbon double bond. Of course, we would represent that in a diagram form, a displayed form such as this. And the presence of the double bond, of course, means that rather than the alkane general formula, we have a modified general formula, CnH2n. So ethene, 2 carbons, 4 hydrogens. Propene, 3 carbons, 6 hydrogens, and so on and so forth. So considering the three-dimensional geometry of the ethenes, that is the shape and bond angles around the carbon atoms. To start with, we need a dot on and cross diagram, and we will see from that that we have a double bond between the 2 carbons, which we are going to treat as a single bond. So we're going to treat it with as the same repulsive effect as a single pair of electrons, and then we have 2 other pairs of the carbon-hydrogen bonds. So effectively, around each carbon there are 3 bond pairs. Now, could you decide on the shape and bond angle? Pause the lesson and decide on the shape and bond angle. So I will reveal what I consider to be the shape and bond angle. So we have a trigonal planar arrangement. Around each carbon, and that bond angle, of course, is 120. So around the carbons from within the double bond of the double bond, the shape, the geometry around each carbon is 120 degrees trigonal planar. Bond angle 120, trigonal planar. We also need to consider the nature of the double bond itself in terms of molecular orbital theory. So that's we're thinking in terms of sigma and pi bonds. And the double bond is composed of 1 sigma and 1 pi bond. So what exactly do we mean by a pi bond? I'm going to model an answer for you. The pi bond is formed by sideways overlap. So this region here, sideways overlap of 2 p orbitals above and below the carbon atom. So that's the 1 pi bond, those 2 regions of orbital overlap. The sigma bond is exactly the same idea as with the alkane sigma bond. Of course, it's the overlap of orbitals directly between the carbon atoms. So to explain or account for the reactivity of the carbon-carbon double bond, we need to consider the bond enthalpies for the carbon-carbon single bond, which is 347, and the bond enthalpy for the carbon-carbon double bond, 612. Now, if we look at the type of bond involved, so the carbon-carbon single is a sigma, whereas the carbon-carbon double is a sigma and pi. Using the data in the table, could you deduce or calculate the enthalpy associated with the pi bond? Pause the video and carry out that calculation. Well, we can see that the difference between a single and a double is a pi bond. The single contains a sigma, the double contains a sigma and a pi. So the difference between 347 and 612, 265 is the enthalpy of bond enthalpy of the pi bond in the carbon-carbon double bond arrangement. So if we look at the sigma bond 347, the pi bond 265, the pi bond is much weaker than the sigma bond. So we explain the reactivity of the carbon-carbon double bond in saying that the pi bond is broken, but the sigma bond is retained. So if we look at this simple diagram here, we've got a sigma and a pi, and on the right hand side we just have a sigma. So the pi bond is broken and replaced with an additional sigma bond for each carbon. So we're moving from a relatively weak bond enthalpy of the pi bond in the double to stronger bond enthalpies, most likely for sigma bonding in the carbons. So if we look at the reactions of the alkenes, there are 4 in the OCR A specification. The first one would be typically a reaction between ethene, an alkene, and hydrogen gas. Could you complete an equation for that reaction? So I've drawn structural formulae, so we have CH2, CH2, ethene going to CH3, CH3, ethane. You produce the displayed formulae for that, for those, please. So here we've got the double bond. A sigma bond is retained in the product between the carbons, and 2 additional single bonds or sigma bonds are formed. The conditions are expected to be known. So a nickel catalyst and heat or 150 Celsius. So if we look at the reaction of the alkenes with hydrogen bromide, for example ethene and hydrogen bromide, then we have ethene. Could you complete the equation, please, of the product molecule? Pause the video and do that now. Okay, so the product molecule will be CH3CH2Br. Could you draw a displayed diagram for that product molecule? So revealing the product molecule, you'll see that the carbons of the double bond have each acquired an additional atom. So each carbon has picked up one of the atoms of the other reactant molecule. So bromine goes to the left-hand carbon, as I've drawn it, and the hydrogen goes to the right-hand carbon. They both pick up one atom. The double bond has been lost, the pi bond has been lost, and we just are left with a sigma bond between the carbons. The reaction conditions, you may recall, room temperature and pressure. So let's give you a problem: propene and hydrogen bromide. Write a chemical equation and draw displayed diagrams of the organic molecule. So pause the video and complete that task. So check your answers against mine. There's the equation. All of the particles of the left-hand side are included in the one product on the right-hand side. conditions of room temperature and pressure. What about the displayed diagrams? Well, we can see if we look at the position of the double bond, those carbons have not changed their position, they're still here, but there's a single bond, and each of them has picked up an additional atom, bromine and a hydrogen. So the third reaction of the alkenes we need to consider is the reaction with bromine. So for example, ethene with bromine. Conditions, room temperature and pressure again. Could you write an equation for that reaction and then the displayed formulae? Pause the video and complete the task. So here is the equation, and the equation written as structural formulae is best explained by the displayed formulae. So the displayed formula adds a bromine to each of the carbons. So each carbon of the double bond picks up a bromine. So each carbon picks up a bromine. So our product is a dibromo, but it's 1,2-dibromo. So we've got bromine picked up on each carbon of the double bond. So the carbons here each pick up one additional atom. The double bond is lost and the single bond remains. Okay, so let's give you a problem, propene with bromine. So write an equation, name the product, and draw the displayed formulae. So could you complete that task? Pause the video and complete that task now. So here is the equation as written as molecular formulae, and the displayed formula, obviously propene, but you'll see that each carbon of the double bond picks up a bromine atom. So each carbon of the double bond picks up a bromine. What is the name? 1,2-dibromopropane. So look back through the three alkene reactions so far. Pause and have a look back through. Okay, so in each case atoms are added to the alkene molecule. Characteristically, there is only one product. So we would define that type of reaction, or classify it, I should say, as an addition reaction. So all the alkene reactions are additions. So let's move on to the fourth reaction of the alkenes. So let's take propene as the example and its reaction with steam. So could you write an equation for that and also displayed formulas of the organic products? Pause the video and complete that task. Okay, so if I reveal the equation, you'll see that we are forming C3H7OH, which is an alcohol. So we're expecting the presence of a hydroxyl group there, so we have an alcohol being formed. What about our displayed products? Well, we've got to get propene right, and we can regard water as composed of a hydrogen and a hydroxyl group. So we can compare that then directly with hydrogen bromide, HBr. We've got HOH. So if we look at our product, we'll see that one of the carbons of the double bond has picked up a hydrogen, and one of the carbons of the double bond has picked up a hydroxyl group. But some of you may not have drawn that product. Some of you may have drawn an alternative. And yes, both those products are possible. Propan 1-ol and the lower propan 2-ol. However, They're not made in equal proportions. We have a major product, which is the propan 2-ol, and a minor product, which is propan 1-ol. Facts that you are expected to recall for OCR A Chemistry A level is, of course, the conditions. Temperature must be greater than 100 degrees Celsius so that we have steam, and the catalyst required is phosphoric acid, concentrated phosphoric acid. But the major and minor issue leads us on to Markonikoff's rule, which brings us to Markonikoff's rule, a rule that predicts the major and minor products of the addition of molecules such as HX to an unsymmetrical alkene. So some terms there will need explanation, but the rule itself is very simple. The hydrogen becomes attached to the carbon atom that is already bonded to the most hydrogen atoms. So we'll do some examples just to clarify that. But firstly, let's look at an unsymmetrical alkene. So here we've got propene. The right-hand carbon is attached to two hydrogens. The left-hand carbon is attached to a methyl group and a hydrogen. So across the double bond, there's a lack of symmetry. So we would call that an unsymmetrical alkene. And looking at the last example that we did as a problem, which was adding steam or water to an alkene, we've got a hydrogen and a hydroxyl group. Applying Markonikoff's rule, can you predict the major product? Draw the structure of the major product, pause the video and complete that task. So here is the major product. You will see that the carbon that already has the most hydrogens, which is the highlighted there, has acquired the additional hydrogen. So the hydrogen here has bonded to the carbon that already has the most hydrogen atoms as per Markonikoff's rule. So the hydroxyl group bonds to the other carbon. However, we may still get some of the other product, and we would call that the minor product. So Markonikoff's rule enables you to predict the major and the minor products. So here's a problem. Predict the major and minor products for the addition of hydrogen bromide to propene. Pause the video and draw displayed formulae and name the products. Okay, so I'm going to reveal, check your answers against this. There is the major product, and we'll see that the carbon of the double bond that has the most hydrogens already, which is the left hand as I've drawn it, picks up the additional hydrogen, and that is the major product. The bromine, of course, adds to the second carbon of the double bond. The minor product, the reverse situation. We have 2 bromopropane and 1 bromopropane as our major and minor products. Okay, so let's move to a second problem. Draw the displayed formulae for the 2 possible products for the alkene as shown. Decide which will be the major and the minor. Pause the video and complete that task. So I'm about to reveal the 2 possible products. We're adding hydrogen to one of the carbons of the double bond and chlorine to the other. Of course, the left hand as I've drawn it will be the major product and the right will be the minor product. Check your answers against those, please. So an introduction to alkene polymers. Alkenes can form covalent bonds with neighbouring alkene molecules. Those reactions result in some long chain molecules, which of course we call polymers. So we might represent that as N-ethene, meaning a large number of ethene molecules will form the polymer or polyethene. The vocabulary there would be monomer for ethene and polymer for polyethene. We might represent it as NC2H4. From your pre-A-level chemistry, could you represent polyethene? Okay, so let me reveal the standard way of representing polyethene. We have a square bracket in which we write C2H4, and then outside of the square bracket we position the number n. As there's one product, we can assume that it is an addition reaction, so polymers of alkenes are referred to as addition polymers. So you might be asked to interpret or draw display diagrams for polymers. So if we draw, for example, 3 ethenes, we would simply link those together to form a long chain of carbon atoms. Exactly the same vocabulary applies: monomer on the left, polymer on the right. You may also be asked to identify the repeating unit. Well, this will be based around 2 carbons. There are 2 carbons in the monomer, and those have come together to form a long chain. So these 2 carbons would represent a repeating unit. So we draw a square bracket around all the atoms involved, including the 2 carbons within the carbon chain. That will be our repeating unit. Of course, it's an addition reaction, so as in all addition reactions, the double bond, or addition reactions of alkenes, the double bond is lost. Just reinforcing the representation of polymerization, we'll see that moving from the left-hand side, the monomer to the polymer, there are basically 3 things that have been done. Place the repeating unit inside a square bracket, extended the bonds from the carbon atoms to beyond the square bracket, and then added an N as a subscript to the square bracket after the square bracket. So that would be our standard representation, but it requires the identification of the repeating unit. So moving on to a problem, here is tetrafluoroethene. Could you represent polytetrafluoroethene? Pause the video and complete. Okay, so let me reveal what I have in mind. So here we have your standard representation, square bracket, subscript N. Note the bonds from the carbon, the double bond is obviously lost, but the bonds from the carbon extend beyond the square bracket. So there's just one additional point to make about alkene polymerization. When the alkene forms the polymer chain, the relationship in space between the side groups, for instance group A and B, and say A and F, is retained in the polymer. So A and B remain on the same side of the polymer chain, and F remains both across and on the neighbour. So the spatial relationship is retained in polymerization. So here's a problem. Draw the polymer polyvinyl chloride. So compare your answer to mine, coming up now. So no surprises, I hope. Let's move on to another problem. Okay, so let's move on to polyvinyl alcohol. Represent polyvinyl alcohol. Pause the video, come back when you're ready. Okay, so polyvinyl alcohol is going to look like this. And it's worth noting that the prediction of the polymer chain is always going to be based around the capital H shape for the alkene. All you're doing is lining up capital H's alongside each other, breaking the double bond and forming the single bond instead, and overlapping bonds reach out. So if you represent your alkene in the shape of a capital H, then you're seldom going to make a mistake on predicting the product. So, slightly harder problem. Could you predict for me or represent polypropene? A displayed diagram, as we have been doing. Think it through carefully. Come back when you have completed it. Okay, so the first thing to do is to get propene correct. Now, as mentioned on the previous slide, if you represent and draw propene in the shape of a capital H, the polymer geometry becomes very straightforward to understand. If you represented propene as a straight line, it's much more difficult to predict the polymer chain. So this is where this technique of drawing the alkene in the shape of a capital H really helps. And final task, polytransbutene. Can you represent polytransbutene? Pause the video, think it through, see if you can come up with the correct version. Okay, so I'm now going to reveal. There is transbutene, so the spatial relationship between the methyl groups is going to be retained in the product. So there is polytransbutene. You might like to think about what polycisbutene might look like. So you're also expected to identify the repeating unit given a polymer chain or section of a polymer chain, and therefore deduce the monomer. So let me just model this one for you. I'm going to identify the repeating unit. Again, looking at 2 carbons in the carbon chain and all the atoms attached. So that's my repeating unit, from which I deduce the monomer. Of course, the monomer must have a double bond. So we lose the 2 bonds that extend beyond the square bracket, and they become the second of the covalent bonds within the carbon-carbon double bond. So there is our monomer from the polymer repeating unit. So let's give you the problem. Here's a section of a polymer chain. Can you identify the repeating unit and from that the monomer? Pause the video, think it through, resume when you're ready. Okay, so I'm now going to select the repeating unit. Again, it's centered around 2 carbons within the long carbon chain. And from that repeating unit, I deduce the monomer. The monomer must have a double bond. Okay, so let's give you the problem this time. Pause the video, identify the repeating unit, and therefore the monomer. Okay, so if I indicate the repeating unit, again, it's centered around 2 carbons in the polymer chain, and therefore the monomer. restoring the double bond, as it were, between the two carbons. Sustainability. What are the benefits of reusing waste polymers? Think back to perhaps some pre-A-level chemistry and write down 3 benefits of reusing waste polymers. Pause the video, think it through, come back when you're ready. So OCR A specifies the reduced use of landfill waste plastics at the moment are taken away and occupy space in landfill. By reusing plastics, less crude oil would be used in the process of making new polymer plastics. And of course, if you reuse waste polymers, then less plastic particles are going to be released into the environment. And this is an important feature of environmental pollution. So, having collected the waste polymers, how might they end up? What are the steps in moving towards generating electricity? What are the steps to reproducing alkene monomers and alkane fuels? And what are the steps towards remolding? So I'd like you to pause the video and think about the steps that there are the necessary steps between the collection of waste polymers and the generation of electricity. Okay, I'm going to reveal the steps involved. Firstly, the combustion of the waste polymer. Secondly, the generation of steam, which are then used to drive turbines to generate electricity. Let's have a look at the second outcome for the collection of waste polymers, which is alkene monomers and alkane fuels. Could you write down the steps between the collection of waste polymers and that outcome? Pause the video, think hard, and come up with the intermediate steps. Okay, so coming back, the first thing is to vaporize the waste polymers, and then a reaction from pre-A-level chemistry, cracking. The cracking of the vaporized polymer could produce alkene monomers and alkane fuels. That is the only mention of the cracking reaction that is featured at GCSE, and it is mentioned here in the processing of waste polymers to produce alkene monomers and alkane fuels. Okay, so the third outcome or goal of waste polymer processing is remolded polymers or plastics. What are the steps involved? Pause the video and write out some intermediate steps. Okay, so moving on. This is the only processing that requires the sorting of polymers by type. So this is a costly step. Having done that, they're chopped, washed and dried. They then energy expenditure on melting and remolded. So we have 2 forms of recycling for our waste polymers, either ending up in remolded or remolded products or alkene monomers, and we have a different type of end use for these waste polymers, which is energy extraction. Should be able to describe those intermediate steps. If you're not confident, I suggest you just replay this slide a few times until it is fixed in your mind. However, chlorinated polymer wastes pose a slightly different problem, for instance PVC, in that they should not be combusted or incinerated, and that's because they will produce hydrogen chloride, which is a toxic product. So it might be possible to remove HCl from the waste gases, but in general chlorinated polymer wastes are not combusted for energy extraction. New types of polymer, which are biodegradable and photodegradable, are being produced. Have a look at this table. Which of these descriptors apply to biodegradable and which to photodegradable? Think about it, make your choices, come back to me when you have completed that. Okay, so if I reveal what is expected, so biodegradable polymers are compostable and they are, for example, made from starch. Photodegradable, the polymer bonds are weakened by sunlight and they are hydrocarbon based. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.